Hello, everyone, and welcome to Day 2 of our IEEE 802.11ax training webinar series. Yesterday, Ben Tien, Senior Director of Technology and Wireless R&D at Qualcomm, gave us a terrific session focused on the features and optimizations introduced in 802.11ax related specifically to the physical or PHY layer. And we'd like to welcome Ben back today. If you have any questions left over from yesterday and you'd like to submit them today, we're happy to receive them. Today, Alfred Asterjati, who is a systems engineer in wireless R&D at Qualcomm, will focus on the medium access control, or MAC layer of the standard. A couple housekeeping items before we begin. At the bottom of your screen are engagement tools that are resizable and movable, so you can move them around to make the most out of your dashboard space. We encourage questions for today's presenters, and you can submit them through the Q&A widget on your screen, and we'll answer as many questions as time allows. Your feedback on this training is very important to us, so before you leave today, we ask that you please complete our feedback survey using the feedback survey tool located at the bottom of your screen. And if you click on the green resources icon at the bottom of your screen, you'll find more information about 802 standards, IEEE e-learning courses, as well as a PDF copy of the presentations. I'll now turn it over to Alfred to get us started.
All right, thank you, Jennifer. Hello, everybody. So as Jennifer mentioned, so we'll continue with the second layer, essentially medium access control, as a follow-up to the presentation yesterday. So the presentation is going to be divided into three parts. The first part is going to be dedicated to multi-user operation. And so as an overview, so we'll first approach the uplink multi-user operation that was introduced in 11ax, and then we'll continue with the improvements to downlink MU operation, and then follow up with a combination of the two operations within the exchange. And then we'll discuss some of the MU feedback mechanisms that we didn't touch through the previous three items. So during this part, you will have learned essentially how downlink and uplink multi-user operation work in 11ax, the different components that enable multi-user frame exchanges, and of course the newly defined feedback mechanisms that support multi-user and improve its performance. So starting with uplink multi-user operation. So before 11ax, in general, stations where it needs to contend for the wireless medium before sending uplink frames. So this was essentially done by using EDCA, so a listen before talk mechanism that is based on random back-off counters. And once you gained access to the medium, you would be able to transmit to your peer station. There were certain features that would allow granting a portion of your TX to a particular station at a time, for example, the reverse direction grant. But anything that was related to multi-user operation itself was not possible prior to 11ax. So 11ax introduced such operation, which essentially enables an access point to trigger multiple stations at the same time. And the trigger frame essentially carries all the transmit parameters that the stations that are being triggered need to use to generate their PHY protocol data unit, which is essentially the PPDU that is going to contain the payloads that are being generated by these stations. And the stations, upon receiving this particular trigger frame, are required to respond after a 6th time, which is essentially in general 9 microseconds, if you will. And they generate the PPDUs in response, which are going to contain their payloads. So essentially using MAC terminologies, they're frames or NPDUs. We do allow multiplexing both in the frequency domain using OFDMA and spatial domain as well using multi-user MIMO. and a combination of both. These parts were discussed yesterday from a PHY perspective. So here we'll assume that the concepts are known, and we'll use them as we go through the descriptions of the exchanges from a math perspective. As a conclusion of the exchange, the access point then you may acknowledge the correct reception of the contents of these PPDUs, of course, if any of the contents is received correctly. And uplink multiplexing essentially leads to increased throughput and reduced latency and improved network performance due to the property of packing multiple transmissions in the same time. So the two figures here show how uplink exchanges were being performed prior to 11ax between multiple stations that are associated with an access point. So you would have each of the stations contending for the medium, and once they would obtain the TXL, they would send their frames. And this would be performed repeatedly until their buffers do not have any more data. On the other hand, with a trigger-based uplink multi-user transmission, it is the access point that triggers these stations at the same time to generate their uplink frames in response, hence optimizing the wireless medium utilization. So the trigger frame is essentially the main frame that was defined that enables the solicitation of these multiple PPDUs from the stations. And here we show the frame format of the trigger frame. And the main fields, if you will, of interest here are the transmitter address, which is essentially the MAC address that identifies the access point so that stations recognize the trigger frames that are being generated by their associated AP. We do also allow an access point to trigger stations on behalf of other BSSs that are being managed as part of a multiple BSSID set. And then we have the receiver address, which is essentially the MAC address of the receiving station. So the MAC address is 6 octets, and it can be either individual, group, or broadcast address. In the case of individual the MAC address, only one station is going to respond, and if the array is set to a group or broadcast address, then the user info list is going to contain the specific identifiers of the stations that are being required to respond to this trigger frame. Then we have the common info field that contains parameters that are common for all the stations that are being triggered. For example, the trigger type, which in general determines the variant of the trigger that we will discuss in more detail in the next slides. It indicates the response PPDU length of the PPDUs that are going to be generated by the stations, and whether carrier sense is required before responding, essentially whether you need to make sure that your carrier sensing is idle or busy. The PPDU bandwidth, the number of the HE-LTF symbols, GI, and the LTF types that you need to use, and so on and so forth. In the user info list, instead, there are parameters that only apply to a certain station, and that particular station is identified by its association identifier that is contained in the user info field itself. The resource unit that needs to be used for including the PSDU within the PPDU that is being generated, and other parameters such as forward error and correction code, modulation and coding schemes, the target received power expected by the access point, and so on. So we'll cover a little bit more in detail these two particular fields in the next slide due to the importance they have in making sure that the PPDUs that are constructed by the stations are correct, and the access point interprets that as valid when it receives them. In addition, the last field is padding, which essentially extends the length of the trigger frame so that it gives time to the recipient stations to be able to process the previous fields of the trigger frame, and are ready to generate the PPDUs in 6 times after the trigger frame. Other fields such as frame control, duration, they are kind of straightforward and are extensively used in 802.11, but frame control essentially identifies the type of the frame and the subtype and other related information, for example, whether the frame is protected, whether there is any fragmentation, whether there is more data, and so on. The duration is used to set the nav for receiving stations so that they do not access the medium while there is an ongoing frame exchange. And the FCS, of course, protects the frame so that upon reception, you verify that the contents there are valid. So speaking of trigger frame variants, which are identified by the trigger type in the common info fields. So we have defined several trigger variants, which are listed here. We'll cover most of them in more detail as part of the exchanges, but we do have a basic trigger frame, which is used to trigger uplink data frames, and these are carried in high-efficiency trigger-based PPDUs. We do have a BFRP, which is a beamforming report poll, and this is used for trigger-based sounding that we'll cover in more detail later. So it's part of solicitation of sounding feedback from the stations. The multi-user block ACK request, which is used to trigger the stations to generate block ACK in response to it, and also these block ACK frames are going to be carried in HETD PPDUs. And we do have then the MURTS, which is used to solicit clear to send frames from the addressed station so that all these recipients clear their navs in their surroundings. The buffer status report poll is used to trigger buffer status reports from the address stations, essentially indicating the amount of data that they have pending in their buffers. GCR MU bar is a variant of the MU bar, but is used for soliciting block acknowledgement for group cast sessions as opposed to individual sessions between the station and the access point, which is the purpose of the MU bar. And then we have the BQRP, which queries the stations in providing bandwidth availability, if you will, on the side of the addressed stations. And the NFRP, which is a variant of the MU feedback that relies on HC trigger-based NDP PPDUs, which do not contain payload, but the limited information that is being provided as feedback is contained in the LTFs of the PPDU itself. So in terms of the common info fields and the user info fields, so the formats are shown here. In general, all trigger variants contain a common portion of the common info field and of the user info field, and a trigger-dependent common info field and a trigger-dependent user info field. In some cases, depending on the variants, either of the two of these trigger-dependent portions may not be present. So, for example, the trigger-dependent common info field is only present in the GCR MU bar trigger frame and is not present on any of the other variants. So in the GCR MU bar trigger frame variant, it contains block ACK request control and information for a particular GCR block ACK session. And as you'll see for the MU bar trigger, that particular information is carried in the trigger-dependent user info fields because the MU bar trigger frame is addressed to multiple stations independently, while the GCR MU bar is not. So the trigger-dependent user info field is actually present in the basic, the BFRP, and the MU bar trigger frames. So for the basic trigger frame that we'll cover a little bit more detail later, it contains parameters that govern the frame aggregation that is permitted in the response HE trigger-based PPDU. And for the BFRP trigger, it contains a bitmap indicating which of the segments of the feedback are being polled by the access point. And for the MU bar, it actually contains the block request control and the information that are related to individual HT immediate block sessions that have been previously negotiated with between the access point and the triggered stations. So as I mentioned, so in response to the trigger frame, the stations are required to generate an HE trigger-based PPDU. In general, there are certain variants of the triggers that generate other types of PPDU. For example, the MURTS that we'll cover later solicits a CTS that is in non-HT PPDU format, which is a legacy format. But so the HE trigger-based PPDU essentially is prepared by the station relying on the information that is decoding in the trigger frame and essentially on the user info fields that are addressed to that particular station. So the AID 12 is going to identify the station that is solicited for transmission in response to a particular trigger frame. And we do have certain AIDs that are not being used by any station that are essentially dedicated for random access. So if a station sees the user info field that has an AID that is identified as for random access, these stations can randomly contend over this random access resource units, which are identified by values 0 and 2045. And if their random counter reaches 0 in any of these RARUs, then the station can transmit its TB-PPDU. Of course, there are chances of a collision in that case, and those collisions are going to be solved at the access point side. But in general, the AID 12 is going to identify uniquely the station that is being solicited so that the collision situations are not going to be there in the general case. The common info field, as mentioned earlier, it contains the remaining subfields that, and the remaining subfields of the user info fields contains the actual transmit parameters that are going to be used by the station to generate the TB-PPDU. So as we mentioned, the MCS, PPDU length, and so on. So this is done for multiple reasons, and one of the reasons is for the station to be able to just see what parameters to use and prepare the PPDU, as opposed to determine locally what is the optimal transmit parameter set that it needs to use to close the link with the access point. So you can think of the trigger-based PPDU as being prepared with the parameters determined by the recipient itself, as opposed to the traditional way that the transmitter determines the transmit parameters. Of course, the generation is going to be prepared subject to the RSSIs and the transmit powers that the access point is providing to the station, and whether the network allocation vector and the clear channel access indicators in the local station, in the responding station, are idle, so that the generation of these PPDUs do not interfere with other ongoing PPDUs of neighboring stations. So the stations are essentially going to generate the TB-PPDU with the parameters that are specified in the trigger frame. If certain conditions are met, for example, the CCA and the NAV being idle, and there are stations that in certain cases may decide to dynamically enable or disable uplink multi-user operation. So the station does not need to respond to a trigger frame if locally the uplink multi-user operation is not enabled. And every time that the station generates this HE trigger-based PPDU, it is required to include in the MPDUs contained in the TB-PPDU an uplink power header control field, which essentially contains the available uplink power headroom for the current HE MCS and whether the minimum transmit power for that MCS is reached. These two parameters can be used by the access point for subsequent trigger frames that are being sent to that same station, and to know whether if the access point requests the station to transmit with more power, then the station can achieve that, or whether the station has reached its maximum transmit power and hence cannot satisfy subsequent trigger frames that are demanding higher transmit powers in the uplink. So here we show the general sequence of the uplink multi-user operation, bearing in mind that the trigger-based CPUs allow both uplink OFDMA, uplink multi-user MIMO, and a combination of the two multiplexing techniques to be deployed by the access point when triggering the stations, so that they perform multiplexing for their trigger-based CPUs. In general, when the access point contends for the medium to send the trigger frame, it is going to use, as traditionally, it is going to use enhanced distributed channel access, so EDCA. In general, the access points are required to use specific ACs depending on the data that they are transmitting or that they are soliciting. The trigger frame, given that it is addressed to multiple stations and may solicit data from different access points, the access point has the freedom to choose any access category to obtain the transmit opportunity for sending the trigger frame. So this is a relaxation of the baseline rule that we have for EDCA access for trigger frames at the access point side. And it is going to specify the resource units where the stations need to respond, and it can also add the random access RUs in the trigger frame so that stations for which the access point knows that they have pending data, the AP allocates individually addressed resource units for those stations. And for stations that the access point does not know whether they have pending data, or that the access point doesn't know that whether they are awake or in those states, allocates random access resource units so that the stations opportunistically attempt to access those random access RUs to send either data in the uplink or just a report to the access points to reserve resource units or units in the subsequent triggering of the access point. So in general, the RU allocation and the numerology that we have allows the access point to multiplex up to 9 stations in 20 megahertz bandwidth, up to 18 stations in 40 megahertz, 37 in 80 megahertz, and 74 stations in 160 megahertz bandwidth. And these stations can multiplex their transmissions, as mentioned, both in spatial and or frequency domains, although the spatial multiplexing is limited to 8. So the stations are going to respond with a PPDU in response to the trigger frame after 6. And as mentioned earlier, this PPDU is constructed with the parameters and constraints included in the trigger frame. And one requirement that we do have to ensure that there is no extra idleness within in between the frames that are being exchanged that would give opportunity to overlapping stations or neighboring stations to gain access to the within this frame exchange. We do require that these PPDUs end at the same time. So this HTTP PPDU by station 1, station 2, and station N, they have to end at the same time so that the separation between the PPDUs and the immediate response that is being sent by the access points of the MBA is 6. So that end time is being satisfied by the use of padding. So after the stations aggregate the MPDUs that they are going to transmit, they can send essentially information that is not useful, is just for filling the rest of the PPDU itself. And as mentioned earlier, so the access point then sends an acknowledgement if any of the MPDUs of the PPDU sent by the stations require an acknowledgement, and of course, if the access point received any of them. So now we're going to go a little bit more in detail on the different variants of the trigger frames that are defined. So for example, for the uplink MU data operation, the basic trigger frame is the only variant that allows stations to aggregate data frames in the HE trigger-based PPDU that they are going to generate. all the other variants, as we'll discuss a little bit more in detail later, they do not allow data frames to be added to the HE trigger-based PPDUs. So the data frames are required to satisfy some limitations and restrictions that are being provided in the trigger-dependent user info field of the user info fields that are included in the basic trigger frame. And these limitations are included here. So we have an MPDU-MU spacing factor, which essentially tells the station to separate the MPDUs between each other in such a way that a minimum amount of time is allocated that would allow the access point to process these MPDUs correctly upon reception. We do have the TID aggregation limit as well, which tells the station the maximum number of TIDs from which the station can include QoS data frames in that particular TB PPDU. So if the access point, for example, tells the station that the maximum, the TID aggregation limit is 3, then the station can only include QoS data frames from up to 3 TIDs. And then we have the preferred AC, which is used by the access point to tell the station from which set of access categories the station is recommended to generate the MPDUs from. This kind of provides flexibility to the station to continue generating QoS data frames depending on its urgency, how long the MPDUs have been in the buffers, for example, but also provides some flexibility to the access point to tell the station that right now I'm calling for higher priority MPDUs as opposed to lower priority MPDUs. So with that information in that is contained in the user info field, the station that generates the HE trigger-based PPDU is going to satisfy the MPDU-MU spacing factor and the TID aggregation limit. These are requirements. The MU spacing factor is needed, otherwise the access point will not be able to parse and decode correctly all the MPDUs due to exceeding speeds of processing if the separation is not satisfied. And the TID aggregation limit is also a requirement due to the fact that each TID has a block accession associated with it in general, and those require memory allocated for the access point to process this receiving MPDUs. And the preferred AC is a best effort parameter that may be satisfied so that the station, if possible, adds data frames only from the access categories that the access point prefers the station to add. And of course, because the access points, to limit the complexity at the access point in terms of memory management of data frames that are not acknowledged yet, we do have a requirement that all QoS data frames that are included in a TB-PPDU, they have to solicit an immediate acknowledgement. That way, it's kind of a set and forget setting for the access point, so that it acknowledges the MPDU. If the MPDUs are received correctly, I can send them to the higher layer and move on, as opposed to storing the received status and wait for the station to ask for the acknowledgement in the future, which would require additional memory. So from an acknowledgement perspective, we do have different options to acknowledge an uplink multi-user data exchange. And here we're showing the two main ones. One is essentially by using the broadcast multi-station block ACK frame carried in a single user PPDU format that is generally in non-HT duplicate PPDU format. And this is because we want this block ACK frame to be decoded not only by 11ax stations, but also by legacy stations, so that they can set their navs correctly based on the duration field of the block ACK frame. And of course, the HE stations are going to be able to obtain the access points received status in the multi-state block ACK frame, of course, if they had sent any data frames in the trigger-based PPDU that solicited this multi-state block. And the other option is by using unicast block frames, and these carried in a downlink multi-user OFDMA PPDU. So the access point sends the block frames in in a downlink MU OFDMA format, so that the stations that are sending the uplink frames can obtain their block in the RUs where they actually generated the uplink frames. So, we'll go a little bit more in detail on the downlink MU operation part that this particular option is going to rely, but in general, the identifiers of the stations and the RU allocation that the stations use to determine where the block are located in the downlink MU PPDU. These are allocated in the 6D portion of the PPDU, which been covered yesterday. And only the stations that are the intended recipients of this PPDU needs to decode it. And essentially parsing post-PHY preamble. The post-PHY preamble of the PPDU is not needed by other stations, so these stations can simply ignore the rest of it. Now, noteworthy to mention that since this is going to be an HE PPDU format, legacy stations cannot understand and cannot decode the contents of this PPDU. So the nav protection that is achievable with option 1 is not achievable with this particular option. So we do have two different options, because depending on the number of stations and the number of MPDUs that are being acknowledged, one option or the other have lower overhead. And that is going to be highly dependent on as I mentioned here, on the number of stations and the number of MPDUs, and of course also the transmit parameters that the access point is going to be using for the PPDU carrying the block acknowledgements. So for the uplink MU data operation, so the sequence here is providing an example as to how the access point is going to populate and specify the preferred ACs and the TID limits for each of the stations. And in this particular example, the stations generate whatever they have pending for generation. For example, station 1 only generates a QA data frame from one TID, and it is actually using the ACVO, which is the same as the preferred AC. And this is because the station has no pending data from other TIDs. Station 2 includes QA data frames from a variety of TIDs, still satisfying the TID limit that the access point is specifying. But the QA data from one TID are the same as the preferred AC. However, the remaining QS data are from an AC that has lower priority. And that is because the station might not have higher priority data, and the trigger-based PPDU is going to have leftover space anyways. So instead of padding the trigger-based PPDU, the station is allowed to send useful data, even though that useful data is from a lower priority. And the station 3 here, even though the trigger is soliciting data frames, the station 3 does not have any data to be sending, but it has a management frame to send in the uplink, and hence uses that opportunity to send that action frame, this add block request frame to the access point, which is essentially frame that initiates a block session setup with the access point. And of course, as mentioned, after receiving the trigger-based PPDUs, the access point is going to generate the, here in this example, I took option 2 as a way to explain the example where the access point generates a downlink or DMA PPDU containing the acknowledgement, multi-state block acknowledgement for the stations in a downlink or DMA format. So with that, we can go to downlink multi-user operation. So downlink multi-user operation was actually introduced in 11AC, and it was relying on multi-user, multi-input, multi-output multiplexing. It did use a group management protocol to group the multi-user stations together. It was done to keep the PHY header overhead as small as possible. However, it leads to certain complications in group management, and used a single user sequential polling to close the uplink with multi-user stations. And here we'll discuss a little bit what we refer to the sequential polling, but in general, it's how you do sounding and how you solicit acknowledgements. So in 11ax, essentially, additional functionalities were introduced to improve the performance. One of them is the addition of the orthogonal frequency division multiple access. The elimination of the need for grouping of multi-user stations and relying on the information that is contained in the file header itself to determine which are the intended recipients of this PPDU. And uses uplink multi-user to close the uplink with multi-user stations so that it avoids having the single user sequential polling. So what we mean by single user sequential polling. So here in 11ax CMU MIMO, the example that is being provided in the slide, you can see that the sounding procedure, for example, the access point needs to poll each of the station individually for their feedback by using, for example, BFRP frames, buffer beamforming report polls, and solicit compressed beamforming feedback. And similarly, also for the acknowledgement, the access point sends individual block ACK requests to each of the stations to receive the feedback in terms of the acknowledgement status. And all these parts are eliminated in 11ax by having a sounding that is relying on the BFRP trigger frame that solicits the feedback in uplink OFDMA, and similarly for the block hacks being solicited in uplink OFDMA as well. And the other difference is that instead of group management to generate group IDs, we do include the stay list, which is the list of the recipients in the downlink LUPPDU itself, in the file header in the SIGB. So these are the three main differences from a signaling perspective between 11ax downlink multi-user and uplink multi-user, downlink multi-user. So starting with the default sequence for downlink multi-user operation, the default sequence is identified essentially as the sequence that relies on self-contained signaling for acknowledging for the acknowledgement generated by the stations. So this self-containment is essentially provided in the downlink LUPPDU itself by aggregating trigger frames along with the data frames to each of the stations. So the access point sends data frames that need an acknowledgement and includes one or more trigger frames to tell the station where to generate that acknowledgement. And this is essentially the default sequence. Different ways that the access point can solicit the immediate acknowledgement from the stations. Of course, the most obvious one is that there is no need for any immediate response, in which case all this is governed by the ACK policy of the QA data frames in the downlink LUPPDU. So if the ACK policy is set to indicate no acknowledgement or block acknowledgement essentially means that the access point is telling the station to store the record status, the receive status of the MPDU, but to not generate an immediate response, because the access point is counting on soliciting that immediate response at a later time. And the other case is essentially at least one immediate response is being generated, and that immediate response is to be carried in an SU PPDU format. So also this one is generally non-HD duplicate PPDU for the reasons we mentioned earlier in terms of legacy compliance or legacy friendliness, if you will, so that they can set their knobs correctly. So here, essentially the SU PPDU is going to contain the acknowledgement of only one station, because if there were to be more than one station, then those PPDUs would be overlapping and colliding with each other. And then we go to the two or more case where the immediate responses are going to be carried in a trigger-based PPDU format, and where the resources in frequency and the other parameters are going to be provided by the trigger frame itself. So to differentiate an ACK policy of normal ACK and implicit bar, that is the one with the SUPPDO format, from the case of trigger-based PPDO format, we use another ACK policy value for the indicating trigger-based ACK, so that the station has a self-contained indication in the MPDO itself as to what type of immediate response the access point is soliciting. And of course, the aggregation of the triggering frame in the downlink MPDO is going to be used to determine what resources to use for the compressed block ACKs and other acknowledgement types that you are being solicited. So on top of the default sequence, we do have an additional sequence that contains the NU bar trigger as a means to solicit these immediate responses. So it can be used for different reasons. One is, for example, if the access point does not have enough room in the downlink MPDO to include trigger frames, or the access point does not receive all the all the block ACKs from the stations. For example, if you solicit 3 block ACKs with a default mode and 2 of them didn't make it in the uplink, then the access point can call again those 2 stations to regenerate those acknowledgements. So all these kind of corner cases can be tackled by the NU bar trigger frame. And the NU bar trigger frame performs essentially the same functionality, plus the addition that it tells the stations to reorder their buffers and send all successfully received data frames to the higher layer. So yeah, very brief overview of the NU bar trigger frame. So all the information that is controlling what type of block ACK is being solicited is carried in the trigger dependent user info field of the NU bar variant of the trigger frame. So the bar control indicates the block ACK request variant. So essentially, you can solicit a block ACK, a compressed version, which is essentially only for one TID, or a multi-TID block ACK request, which is soliciting a multi-state block ACK frame that contains block ACK bitmaps for multiple TIDs. And then the bar information is essentially used by the recipient to prepare the block ACK frame, because it contains, for example, the starting sequence number, and also to reset the block ACK scoreboards. And as a response to the NU bar trigger frame, essentially the station generates the solicited block ACK frame variant and resets the block ACK scoreboards and moves its starting window to the starting sequence number specified in the bar. So an additional noteworthy difference between the NU bar sequence and the default one, so if we go back, is in the default sequence, you can also solicit an ACK frame itself. So instead of a block ACK, with the NU bar, you're not able to do that. So if station 1 was to be solicited an acknowledgement, then the access point would not be able to solicit that ACK itself, because the bar always requires a block ACK session set up between the AP and the station. So from a downlink multi-user perspective, especially for downlink MU MIMO, we rely on sounding. So downlink MU MIMO, and of course SU, the relies because of beamforming, they require the knowledge of the receiver's channel state, so that the beamformer can use the received feedback to compute a steering matrix that is going to be applied to the PPU itself, so that it can optimize the and increase the likelihood of reception at the recipients. In 11ax, we have defined 2 feedback mechanisms for sounding. One is non-trigger based, so it's a non-TB sounding, which is generally used for beamforming, and the trigger-based sounding, which is generally used for multi-user operation. And both of them allow the beamformee to measure the channel using a training signal transmitted by the beamformer and send back a transform estimate of the channel state, which is then going to be used by the beamformer to derive the steering matrix. So we'll cover a little bit in detail both of these modes, but essentially the idea here is to provide a transmitter of channel estimates at the recipient so that when I generate the PPDU, that PPDU has the highest chance of reception at the recipient because it's based on the channel quality indication of the recipient. So the two sequences are shown here. One is the trigger-based sounding, and the other one is non-trigger-based sounding. So starting with the non-trigger-based sounding, it consists of 3 frames within the exchange. So there is an announcement, which essentially announces that the sounding is to be performed. Then there is the NDP, which is going to be used for estimating the channel, and the HE compressed beamforming and CQI, which is going to contain the estimates. And of course, in the trigger-based sounding case, the last frame is replaced with a BFRP trigger and multiple CBFs being sent by the beamformee, such that you can obtain in one shot the channel estimates of all the beamformees, and then you can use it for your downlink MU MIMO PPDU preparation. So the non-trigger-based sounding, so the differentiation is between non-trigger-based sounding and trigger-based sounding starts from the NDP announcement itself. So we rely on the RA fields of the NDP announcements to indicate that, for example, if the RA field is individually addressed, then this is non-trigger-based sounding, in which case only contains one stay info field because it's addressed only to one station. And for the trigger-based sounding, the RA field, as we'll see later, is set to the broadcast MAC address, so it's addressed to multiple stations. So as non-trigger-based sounding sequence goes, this can solicit 2 feedback types, essentially, for single user, full bandwidth, and multi-user full bandwidth. However, we do have a mode which is for partial bandwidth feedback, which is allowed in the trigger-based sounding, but not in the non-trigger-based sounding. And the NDP announcement is allowed to be carried in any single user PPDU, but as you might have noticed, in general, we prefer to use the non-HT duplicate PPDU format to help legacy stations to correctly defer to the NAV. So this is also the case in this particular mode. And then, of course, followed by the sequence is continued by an HE sounding NDP that has the same bandwidth as the HE NDPA. And then the CBF, which is essentially going to provide the feedback depending on the combination of the code book, NGs, whether CBF is segmentation is used or not, depending on what the access point or the beamformer is soliciting in the sequence. So the trigger-based sounding is the main difference is essentially that you can poll multiple beamformees to generate their feedback. The differentiation is that initiates the trigger-based sounding is based on the RA field set to the broadcast MAC address. And of course, it's going to contain more than one info field because more than one station, so multiples are being solicited. And of course, also in this particular case, the difference is that instead of having the CBF from one station being sent immediately after the NDP, you do have the access point sending a BFRP trigger frame that not only specifies what resource units and RU allocations and the duration of this trigger-based PPDU is going to be, but it also specifies which of the segments are being polled, because in general, the CBF can be pretty long. It can exceed in the order of kilobytes and even megabytes in certain cases, especially for MU MIMO. So the access point can tell the station which of the segments to transmit in each of this sequence. And so because segmentation is allowed, so if you're missing some segments or if you have multiple stations that you want to do multiplexing, you can have multiples of this BFRP CBF sequences within the same TX. So now if you think of ways to combine uplink multi-user and downlink multi-user, with a certain added level of complexity, because if you think of the downlink multi-user with an acknowledgement that can be a combination of downlink and uplink, we do have a sequence which is called MU cascading sequence. This particular sequence requires a little bit more processing power from the access point, because in a particular sequence, you are going to find not only the data from the station, but also an acknowledgement for your downlink data. And then it is going to be followed by a trigger that needs to contain the block acknowledgement for the previous data and eventually other data to the same station. So all this requires additional processing, because you are going to involve multi-processing in different components, so block access scoreboard maintenance, buffer management, because you have to prepare the MPDUs and append them to the AMPDU, and you also have to worry about the trigger preparation for the subsequent data. So this particular mode is essentially optional in 11ax, although it increases multi-user aggregation efficiency within a SIG. So other MU feedback mechanisms. So we discussed uplink multi-user and downlink MU operation, and we focused a little bit more on the two main MU feedback mechanisms for which we all block ACK frames with the MU bar and the sounding feedback with the BFRP. So now we'll go a little bit over the details for the remaining variants of the trigger frame and the reports that can be triggered by them. So the first one is MURTS probing. So it's using the MURTS trigger frame. This particular feedback mechanism is essentially targeting on improving the protection of the SIG sub from neighboring stations. So traditionally, we use a request to send, clear to send sequences to set the navs in the recipient and at the transmitter so that nobody else can transmit on top of your transmissions. However, in a multi-user setting, to set the nav for multiple stations, you would need to send a sequence of these RTS CTSs so that you can protect the now you can protect the medium from the neighboring stations of multiple stations. And this is not very efficient because it creates a lot of overhead. So in order to avoid that particular issue, so to reduce the overhead, 11ax introduced the MURTS trigger frame, which essentially solicits CTS frames from multiple stations. So how does that work? So the access point sends an MURTS, and all the stations that are being addressed by this MURTS are going to generate a clear to send frame. The stations that are the intended recipient of the MURTS are essentially going to be identified by the user info field. And we do require the CTSs to always include the primary channel, because the primary channel is being used by any of the stations that are associated with that access point. So if you're not clearing the primary, you may have multi-channel hidden node issues. And the stations, once they receive the MURTS trigger frame, they will respond with a CTS frame if, of course, the medium is free. Free meaning that the energy detect CCA is idle, so you do not detect any energy in the channel. And also your nav is zero, so essentially you're sure that nobody else from your neighboring stations have caused you to defer for a certain amount of time because there is an ongoing transmission. Now, as usual, because the CTS frames need to set the nav also of legacy stations, they are sent in non-HT duplicate PPDU format eventually, and they cover the whole pole channel width so that you're protecting all the bandwidth where the access point is intending to send the downlink or the trigger-based PPDU sequence. So now, because the CTSs that are being generated by the stations, it is going to be difficult for the access point to determine which of the station responded because the CTSs, they only have a receiver address, which is the address of the access point. the access point is going to have the ambiguity as to which station responded, so it has to have a best guess, if you will, of which of the stations acknowledge this MURTS trigger. But the most important thing that is needed to be taken care of is that the CTSs have to have the same content, so that the superposition of the bits is such that the FCS of the CTS itself at the AP side passes. Otherwise, the access point will not be able to determine whether the packet is corrupted or not. So to achieve that, we do use a scrambler seed at each of the stations that is a replica of the scrambler seeds that is obtained from the MURTS trigger frame, so that they have a common reference. So going to the next feedback mechanism, which is buffer status report. So buffer status reporting, as the word itself says, solicits reports from the stations in terms of their buffer status. So how much pending data they have for transmission in the uplink. And that is going to be used by the access point essentially to allocate the uplink multi-user resources efficiently, and also calculate how much to give to each of the stations. We have two different ways of signaling the buffer status reports from the station. So we can either use the QoS control field, which is containing the buffer status report as part of the queue size, or the HT control, where we have the BSR control field in the HT control. So the difference between the two is, first is the amount of information that it can carry, because the queue size is only 8 bits, and the BSR contains 2 queues, each of them with 8 bits, and the QoS control is on a per TID basis, so you can report the buffer status for each TID, but no more than one in the same MPDU. And for the BSR, you can actually report the whole queue size, and also the queue size of the highest AC that you have pending buffered units, essentially. And of course, because of different scaling factors that we have, the queue size of the QoS control can report up to 64K approximately. Instead, the queue sizes in the BSR can report up to 8 megabytes of payloads. So in terms of sequences, we do have 2 sequences for BSR. One is unsolicited, so the station can report buffer status reports at any time that it sends data. And the solicited BSR, which is essentially delivering the buffer status reports only in response to the BSRP trigger frame. The station can use either of the two or both. And anytime that the access point receives any reports, is going to use this report to essentially prepare the uplink resources for the station, so that the uplink multi-user resources are used efficiently. So the figure here shows both the cases of having a particular station 3 that reports buffer status in an unsolicited way, and station 1 and 2 that report their buffer status in a solicited way. And then the access point use that information to prepare for the next uplink MU data exchange. So bandwidth query report is very similar to the buffer status report. The difference is that now you're querying the stations in terms of their bandwidth availability. So in a 160 megahertz band, you can indicate which of the 20 megahertz subchannels are idle or not, so that the access point can use that information when it allocates the resources to each of the stations. So in terms of the example, for example, you have a similar indication from a station that only a subset of the channels are available on its end, and this is being done by an unsolicited BQR. And then station 1 and station 2 are being polled by the access point to provide their BQR status, so their bandwidth status. And with that information, the access point uses it so that the data to station 2 are being sent on an RU that was indicated as idle by station 2. And similarly, the data to station 1 is being sent to an RU that is idle, and same thing for the uplink. So these bandwidth query reports are being used by the access point to send data and solicit data from the stations in sub-channels that are idle. So the last feedback mechanism from a multi-user perspective is the NDP feedback report polling. So this is similar to what buffer status report is doing. However, the NDP feedback report polling enables the station to solicit feedback from a larger number of stations compared to other multi-user mechanisms. For example, as I mentioned earlier, we can only solicit 9 stations with a BSRP in a 20 megahertz channel. With NFRP, this goes to 36, so a 4x increase. And this is proportionally increasing for each of these particular bandwidth combinations. However, it comes at the expense that now you do not have the full information of the buffer status of the station, but you only have an information of the type yes or no. For example, hey, do you have more than 256 octets in your buffer or not? And the station's response yes or no. And then that information is, of course, going to be used by the access point to allocate your subsequent uplink MU exchanges. So the mechanism itself is a little bit generic, but currently we only have defined one particular feedback type, which is essentially a resource request, essentially for uplink MU. So the spatial report in a binary form with a bit set to 0 to indicate that the station is awake and pending data for delivery, and that data for delivery does not exceed a buffer threshold that the access point announces to everybody in advance. Or is set to 1 to indicate, yes, I'm awake and pending data for delivery, which essentially is going to exceed that buffer threshold. So there are 3 exchanges that can, 3 responses from the station, essentially. 0, which is essentially I have data but limited. 1, which is I have data and exceeds what you're expecting. And no response, which means I'm not there and I don't have any data. So that is for part 1. So we went over how uplink MU operation works and the various uplink MU sequences, and went over the detail of the trigger frame format, variants and contents, and then we continue with downlink MU operation and the various downlink MU sequences we have. And then we covered the general concept of the different feedback mechanisms that we have for improving MU performance. So I think that's for that for part 1. So I can see if there are any questions, and then we can take a break. So does the beamforming literally direct the RF waves like the Starlink user ground antenna? I'm not very familiar with the Starlink user ground antenna, but essentially what it does is it allows the beamformer to obtain the feedback from the recipients and then use specific orientations of the beams that you're sending to the recipient to maximize the RSSI at the recipient, so that the signals from multiple antennas can create a constructive wave at the recipient as opposed to a destructive wave. So a pretty straightforward multi-user, a multi-input, multi-output operation. So yeah, we can take 3 minutes break, and then we'll continue with part 2. So we can reconvene in 10:07 Pacific time. All right, so we can start with part 2, essentially. So during this part, we'll start discussing a little bit on the enhancements that were introduced to frame aggregation at the MAC layer. Several enhancements to the block acknowledgement mechanisms, in particular the frames that carry this acknowledgement, and some channel access enhancements as well. So at the end of the session, you'll have learned how the different frame aggregation options that are available for 11ax work, and also a little bit of background how frame aggregation in 802.11 works as well, how dynamic fragmentation works as well, which was introduced in 11ax, and the enhancements to block ACK and channel access. So an overview of frame aggregation, kind of giving you an idea as to how the also the data being provided by the upper layers is being delivered through the MAC layer and then to the PHY layer and then over the wireless medium and then to the receiving end. So you can think of this as a top-down approach of aggregation from an 802.11 perspective. So all the payload that we receive from the upper layer, so think of the Ethernet packets, they are encapsulated, if you will, or they are represented as MSDUs from an 802.11 perspective, so they are called MAC service data units. These MAC service data units can be aggregated at the MAC layer at the MSDU level, in which case we call them as aggregate MSDUs. And these aggregate MSDUs can be carried in the frame body of the MPDUs of the MAC protocol data units, or we can carry just the MSDU itself in the frame body. And then we do take several of these MPDUs and pack them together in an aggregate AMPDU. So the aggregate AMPDU is relying on the AMPDU format, allows multiple MPDUs to be carried in the same PSDU, so in the same PHY service data units or PHY layer service data units, which in turn with the inclusion of the PHY header is defined as PHY protocol data unit. So as you can see, we have two different aggregation modes at the MAC layer. So we have AMSDU aggregation and AMPDU aggregation. So one of the differences between the two is that AMPDU aggregation is more robust than AMSDU because each of the payloads are protected with an FCS, as opposed to the AMSDU, which essentially relies only on a single FCS for protection. And of course, AMPDU also allows a station to aggregate other types of MPDUs in the same AMPDU, for example, control frames, management frames, and so on, which is not possible with AMSDU aggregation. So from a PHY perspective, since we mentioned quite extensively the non-HD PPDU format and the HD PPDU format, so it's noteworthy to kind of have an idea of the limitations and flexibilities of each of these PPDU formats. So the non-HD PPDU format does not support aggregation of MPDUs. So you cannot use AMPDUs in a non-HD PPDU. It can only contain one single MPDU. However, that MPDU may contain AMSDU. So in a non-HD PPDU, you can actually aggregate MSDUs only. The HTTP PPDU format supports by default AMPDU, and each of these MPDUs may contain AMSDU. So HTTP are more flexible in terms of the different aggregation modes they can support. So given that we're going to discuss to more extent the aggregate MPDU, so we're providing here the format of the AMPDU. So it consists of multiple AMPDU subframes, and then at the end, it has an end of frame padding. Each AMPDU subframe is preceded by an MPDU delimiter, which contains information that is relevant to that particular MPDU. So you have the MPDU length itself. You have the EOF field, which indicates whether this MPDU, for example, is a single MPDU or whether it's part of a multiple MPDU setting or whether it's carrying essentially nothing. So the MPDU is absent. And we do use that particular combination to identify pre-EOF padding. So this pre-EOF padding is essentially used to satisfy the minimum spacing between MPDUs. When we discussed earlier the MU minimum spacing factor, this is how the station achieves that there is enough separation between the MPDUs in the MPDU. And then we do have end of frame padding, which is identified by a setting of the EOF field to 1 and the length equal to 0 to differentiate it from the pre-EOF padding, which gives to the station enough processing time after the last MPDU so that it decodes the packet and updates the block-ACK scoreboards and generates the immediate response. The EOF equal to 1 and the length greater than 0 identifies a single MPDU, which kind of mimics the properties of an MPDU carried in a non-HT PPDU. And this is mainly to separate between soliciting an ACK frame and soliciting a block acknowledgement frame. So the block acknowledgement frame is solicited by an AMPDU structure or construct, and the ACK frame is solicited by a single MPDU construct. And then we have the CRC, which essentially protects the previous portion of the MPDU delimiter, so that you know that, for example, the MPDU length is correct or not. And we have the delimiter signature, which helps the station while parsing. If, for example, there is an error in a particular portion of the AMPDU, you keep looking for the delimiter signature. If you find it, then you have most likely found another AMPDU subframe so that you can still decode the remaining portion of an AMPDU, even though the preceding portion was corrupted. And so the pre-EOF and EOF padding can also be used to ensure that the PSDUs end at the same time, which we discussed earlier. So there's a feeling the PPDU to align between multiple stations. So in terms of enhancements to frame aggregation, so everything we spoke up to here is kind of aligned to what baseline is doing. So we are relying on baseline aggregation of MPDUs to perform the enhancements in 11ax. So the enhancement is that we increase the aggregation capabilities to up to 256 MPDUs as opposed to 64 MPDUs, which is in a baseline. And this is essentially for a single TID. We do allow multi-TID aggregation as well, which was a limitation in legacy that allowed only one single TID. So we can aggregate in the same AMPDU up to data frames up to 8 TIDs. And then there are some added flexibilities. For example, that within an AMPDU, we can still include MPDUs that solicit in an ACK frame as opposed to a block ACK frame, which essentially allows aggregation of a management or control frames with QoS data, which was not possible before, and dynamic fragmentation, which was not allowed in legacy, and it is useful, as we'll see, for instead of padding, so to increase the PPDU, to reduce the PPDU overhead. So the multi-TID AMPDU variant, so we have two variants. One is the non-ACK enabled multi-TID AMPDU. Essentially, all the MPDUs that are contained in this AMPDU solicit block acknowledgement. So there will be a block ACK for each of the TIDs, and up to 8, of course, depending on how many you have negotiated. And the ACK enabled multi-TID AMPDU, which along with the MPDUs that solicited block acknowledgements, it allows at most, it allows one MPDU that solicits an acknowledgement. So when you generate the immediate response, you are going to see let's call it an ACK frame, but it's not really an ACK frame, but you can see an ACK plus multiple block ACK bitmaps. And this is going to be carried in the multi-state block ACK frame that we will cover in detail in a bit. But so this is essentially the difference between the two variants. And in terms of medium access to content for generating and for sending this frame, so traditionally, once you gain access with a particular primary AC, you are only allowed to send data frames from that particular AC. So you cannot send data frames from other ACs. For the multi-TID AMPDUs, we do allow the station that gained access to a particular AC, which became the primary AC, to also aggregate TIDs from that same AC, but also from ACs that have higher priority. So going to baseline fragmentation. So baseline fragmentation allows an MSDU that is received from the higher layer to be partitioned into multiple fragments, and each of these fragments are to be carried in a separate MPDU. And all the fragments, except for the last one, are required to have the same length. So if you have a MSDU that is fragmented into 4 fragments, then you will have fragment 1, 2, and 3 having the same length, and the last fragment that may have the same length or less. So if you can think of the discussions we had earlier about the PPDUs ending at the same time, having this restriction that the fragments have to be at the same length, then you may realize that this particular mode is not that useful to be used as padding, because your amount of leftover portion of the PPDU is going to depend on multiple factors, and it's going to be drastically changing from one PPDU to the other. So you cannot rely on this type of fragmentation to fill in the leftovers. And also the baseline does not allow static fragments, which are these baseline fragments, to be carried in an AMPDU. So if you were to use fragments, you could not aggregate them along with other MPDUs, which significantly reduces the usefulness of the feature. So to essentially to address these issues and essentially to expand a little bit the flexibility and usefulness of fragmentation to be used instead of padding, so 11ax defined dynamic fragmentation, which essentially relies on baseline fragmentation but removes these restrictions. So dynamic fragmentation essentially allows 3 main things. One is that the fragments can be of any size, so they are not restricted to be the same, so that you can use them as instead of padding. The other part is essentially that you can aggregate them in an AMPDU. And the third aspect is that they can be acknowledged with block acknowledgements as well, which was not possible. So all these particular functionalities, added functionalities, allow dynamic fragmentation to be an efficient way for using the allocated resources in MU operation, because you're essentially aggregating fragments of an AMPDU instead of padding. And also it can still be used as a means to closing the uplink for limited range devices. For example, when you are a device that is far away from the access point, and the access point is allocating you resources that are too small for containing a full MSDU, as a station you can only send 1 fragment. However, if you were to use the legacy fragmentation, then on the next fragment that you were going to use, you had to use the same size fragment as the previous one, which is a significant restriction for using those resources to the best of your capabilities. However, because of all these added flexibilities, you have also additional complexities of the system, because you have to generate fragments on the fly and so on. So we have defined different levels of fragmentation for 11ax. One is, of course, no dynamic fragmentation at all. And the other one is essentially a single fragment in an AMPDU that solicits a NAC. Think of this case of addressing the uplink resource limitation. And then level 2, which is essentially a single downlink, a single dynamic fragment of an MSDU in an AMPDU that solicits a block ACK. So you can have fragments of other MSDUs on that AMPDU as well. so you can pack as many as you want. And then we have another level, which is allowing up to 4 dynamic fragments of an MSDU in an AMPDU that solicits a block ACK. The difference between level 2 and level 3 is that once you allow multiple fragments of the same MSDU in the same AMPDU, then you need to modify the block ACK bitmap to represent those received statuses. So with that, we go to the block acknowledgement enhancements. So as mentioned earlier, so we inherited the ACK frame from legacy and the compressed block ACK. The ACK acknowledges a single MPDU, and the compressed block ACK acknowledges up to 64 MPDUs in the baseline. In 11ax, we took what we had and we enhanced the compressed block ACK frame, and additionally defined a new multi-state block ACK frame to essentially support all the frame aggregation enhancement that we discussed earlier, and also to support the acknowledgement of frames sent by the multiple stations. This is for the uplink multi-user data exchange that we discussed earlier. And of course, based on the different received statuses of the different aggregation modes that you had of the MPDUs of all the stations, you can also play with the frame formats to reduce the acknowledgement time in these different settings. So starting with the compressed block ACK frame, so a general overview of what was added, which is essentially support of 256 block ACK bitmaps and support for dynamic fragmentation in its both flavors. So level 2 and level 3, because level 1 can be acknowledged with an ACK frame itself. But level 2 and level 3 essentially require the generation of a compressed block ACK frame, and the different combinations of the block ACK bitmap length are essentially indicated by an overload of the fragment number fields of the compressed block ACK frame, which was previously not used. So different settings of these 4 bits indicate the length of the block ACK bitmap that is being carried. And for example, whether you are acknowledging dynamic fragments of level 3. For example, those two when you set the bit 0 to 1, you're indicating the block ACK bitmap length, but also that you're acknowledging dynamic fragments of level 3. And given that this is a level 3 acknowledgement, your maximum number of MSDs that can be acknowledged is decreased by 4, because now you have that each MSDU has 4 bits representing the received status of each of the fragments. Multi-state block ACK, you can think of it as an expansion of the compressed block ACK with additional properties or with added flexibility. The added flexibility is that now you can acknowledge frames sent by multiple stations, and this block ACK information that we had earlier, now it's repeated multiple times per AID and TID. So these tuples can identify one particular station and the particular TID of that particular station. So you can have different block ACK information bitmaps, if you will, for multiple stations and for multiple TIDs. So you can use this multi-state block ACK frame for uplink MU data operation and for multi-TID AMPDU acknowledgement, and a combination of both. So to differentiate the different contexts of what you're acknowledging, so we're relying on these ACK type fields, and of course it's going to depend also on the TID if it has any meaning, because you can have a block ACK context, so essentially you're acknowledging data that is soliciting a block ACK frame, so you're going to have a block ACK bitmap in that particular case. You're going to have the ACK context, which is essentially mimicking the ACK frame. In that particular case, you're acknowledging only a single data frame, and as such, you're not going to have a block ACK bitmap. There is another variant or another context, which is the all ACK context, which is essentially indicating that all the MPDUs in the AMPD were received successfully. So then I don't have to send the additional overhead of the block ACK bitmap and block ACK starting sequence control. I can simply say that, okay, everything of that A MPDU was received correctly. And then we have a particular combination for the PS pole ACK context, which is and for management frames. So traditionally, control frames and management frames do not have a TID identifier, so you would not be able to acknowledge them as part of the block hack acknowledgement. So what 11ax did is to reserve a value of the TID, which was currently unused, to specify the acknowledgement of a management or PS pole frame. So in terms of the frame formats, so here we essentially discussed the different contexts, but as you can see, the block ACK bitmap has different lengths as well, even more than what the compressed block ACK frame had, which had only 2 possible combinations, so 64 and 256. Here we have anything between 0 and 256 bits. So to indicate those particular values, we use a similar encoding as for the compressed block ACK frame by using the fragment number, but the combinations are larger in this case because we also cover the case of 128 bits and the case of 32 bits. And this was done to add the flexibility to the multi-state block ACK frame to allow the reduction of the overhead that would be coming by the use of the multi-state block ACK frame with large block ACK bitmaps. So as you can see, the frame is flexible enough to essentially allow the acknowledgement of single MPDUs, single TID-A MPDUs, multi-TID-A MPDUs with their different variants, ACK-enabled, non-ACK-enabled, and of course can be also sent in response to uplink MU data frames sent by multiple stations. So it kind of fits a one solution fits all type of frame for uplink multi-user operation and multi-TID operation. So that kind of concludes the block ACK enhancement. So going to the channel access, so starting with the BSS color. So BSS color is essentially a field that was introduced in the CGA field of the PHY header of HCPPDUs. And the purpose of it is essentially to differentiate PPDUs that are generated by your BSS and PPDUs that are generated by the BSSs, by other BSSs. So if you think of it here, even from a color representation, if you are a station that is operating in AP1, you would have color red, which would be identified, let's say, by BSS color value 1, and then AP2 color green, that would be identified by BSS color 2. So every time that you see a PPDU that has BSS color 2, you would know that that particular PPDU is not generated by your own AP or by stations that are affiliated to your own AP. So the benefit of this BSS color information is that it helps the receiving station making decision for nav setting, intra-PPDU power save, and spatial reuse. So spatial reuse, we discussed it yesterday from a PHY perspective. Today we'll go a little bit on its uses for nav setting and intra-PPDU power save, so completing the picture for this particular functionality. But so it has several benefits, especially in dense deployments, because it improves network capacity and the user experience that is due to spatial reuse. So you do not have to differ over a particular PPDU that you could reasonably transmit on top of it without causing interference. And of course, other benefits as well as, for example, the power consumption reduction, because if you receive a PPDU from your own AP that is addressed to somebody else, you might as well just go to dose state during that time instead of staying awake. So now the BSS color is not unique across all the wireless LANs all over the world. We only have I believe 6 bits for the BSS color. So essentially we can cover a range of between 1 and 63. We're using the value 0 as BSS color for everybody so that you can do inter-BSS communications. So the values 1 to 63 are the actual colors that are identifying BSSs. The BSS color is chosen by the access point And so when you boot up your network, the access point searches for other neighboring APs, determines what BSS colors they have, and essentially chooses a BSS color that is different from those of the OBSS APs. It can also rely on reports from the stations that are associated to it as well to make this choice. But there may be cases where you run out of BSS colors because you have, for example, more than 63 BSSs in your neighborhood. In that case, you're required to choose a color that is the same as somebody else's, in which case the access point can disable BSS color once it detects that there is a BSS color collision. And you can keep this disablement for as long as this collision persists. So when this BSS color is disabled, all the features that rely on BSS color are essentially disabled by the stations as well. Now, if there are cases where the neighboring AP that was using the BSS color that had filled the range essentially has left or has turned off, then you are free to essentially choose that available BSS color, which would require a change on the BSS color. So there are mechanisms that allow the AP to change the BSS color and announce this new color to the stations, so that the station starts using the new BSS color, and once the BSS color change has completed, the stations can initiate using the features that rely on the BSS color itself. So the other part that relies on the BSS color is two-nav operation. So as mentioned earlier, so the nav purpose is if you hear a PPDU from a peer device, it's not intended to you, and it's telling you that you have to defer for 5 milliseconds, you are required to defer for 5 milliseconds. And you update that value as along with the PPDUs that you're receiving, so that the last frame of that exchange can tell you, okay, you have 0 seconds left. So after that, the nav is idle, and then you can start contending and hopefully gaining access. This was one nav timer for everybody, baseline. For 11ax, we introduced the concept of 2 separate nav timers. One which keeps track of the nav set by the PPDUs generated within the BSS, so from essentially the access point and stations that are associated with that access point, and one that keeps track of the PPDUs generated by the other BSSs, so everybody else but your access point and your BSS. Stations are required to keep 2 nav timers. The access point is free to maintain 1 or 2 nav timers. The reason why the stations are the ones required to keep 2 nav timers is because they are going to benefit from the 2 nav timers when generating trigger-based PPDUs in response to trigger frames. The reason for that is that if the station has the intra-BSS nav set, it can ignore it if it is triggered by the access point. Now, if you were to have a station that only uses one common nav, which is going to be by default the basic nav, then you are not going to be able to respond to a trigger by the access point. So losing opportunities in transmitting data in the uplink, even though those opportunities are there for you to use. So that is the intra-BSS nav, essentially stores values that are generated by duration fields in PPDUs within the BSS. And the basic nav is the legacy network allocation vector, and it stores values from inter-BSS PPDUs or from PPDUs that you cannot classify as neither of them. So this particular nav is the legacy one, so you cannot ignore it unless there are specific requirements in terms of CS required bit in the trigger frame, which can be set to 0, so you're allowed to ignore the nav of other BSSs only in specific conditions. And the simplest thing that we can mention is, for example, that the trigger-based PPDU that you're going to generate is very short. For example, if you're generating a PPDU of 50 microseconds, then the access point is allowed to give you the freedom to ignore the nav. So the 2 navs can be applied for multiple reasons. So you can have a selective nav truncation based on intra-BSS or inter-BSS CFN frames. So it gives you flexibility on truncating only your nav without affecting in basic knobs. So other DSSs are not going to rely on that particular information, and your stations especially are only going to truncate their knob without touching the basic knob. As mentioned yesterday, by being spatial reuse relies on the knob as well, because stations may transmit despite a non-zero basic knob, subject to spatial reuse conditions, of course, and they don't really rely on the intra-BSS knob. And as I mentioned, the uplink MU operation where as a station, you're free to respond to a trigger frame despite a non-zero intra-BSS knob. So here the example covers the two main aspects for the two knobs to exemplify the behavior. One is essentially the T-stop truncation of your inter-BSS knob. So essentially, as a station 2, as a station 1 that is associated with AP2, this is based on the colors that we're using here. So color green identifies stations that are associated with AP2, color red identifies stations that are associated with AP1. So as a station 1, once you receive a trigger from AP2, which is your AP, you set the intra-BSS knob for the amount of time that the AP told you. And then the AP is interacting with station 2, and then all of a sudden there is a trigger frame from AP1 that sets your basic knob. Now that AP1 tried, station sent the trigger-based PPDU. For some reason, it failed to be received by the AP1. The access point 1 decides to end the T-stop. The end of the T-stop is achieved by sending a CFN. Upon reception of the CFN, station 1 now truncates the basic knob at the end of the CFN, while still continuing to keep the intra-BSS knob. The intra-BSS knob is going to be used for all the time unless the AP2 triggers the station, which occurs at the last exchange where AP2 sends a trigger and the station 1 ignores the intra-BSS knob to generate the trigger-based PPDU. So the next enhancement for channel access is the introduction of multi-user EDCA. So today, we in 802.11 rely on EDCA parameter sets to control the priority that stations have when contending for access. And we use the baseline, or here I call it legacy EDCA parameters. So any station that associated with an access point is required to use contention window parameters that are advertised by this legacy EDCA parameter set. And all stations are equal. So it's broadcasted to all of them, and all of them use the same values. Now, with the introduction of uplink MU operation, we have the stations sending uplink frames in response to a trigger frame kind of for free, because they do not have to do any EDCA contention. They send them as an immediate response to the trigger frame. And still giving them the freedom to contend using EDCA to send other uplink frames. So this kind of behavior puts these stations in direct competition with the access point, because the access point itself is trying to gain access for downlink and also for sending additional triggers. But you have also these stations that are already being served trying to access to send their additional data that they might have. So this can create opportunities of collisions, reducing the overall throughput of the network, and also miss multi-user opportunity, because if these stations are able to send their uplink data by themselves, then they are not going to use the triggers sent by the access point. So the system is going to suffer due to inefficient allocation of the resources, because now it's not the access point polling the stations, are the stations just accessing on their own. So we're missing the coordination opportunity or the scheduling opportunity that uplink multi-user was giving. And of course, so now if these stations are double dipping uplink MU and contention, then it would give them unfair advantage with respect to other stations that are not capable of performing both functionalities. So 11ax introduced two EDCA parameters, one which is legacy and the other which is MU EDCA parameter sets. These are parameters that differentiate the access of the station. So in general, the access point is going to provide higher access with legacy EDCA parameter sets and lower access with the MU EDCA parameter sets because 11ax stations are already being triggered for their uplink frames, so that you kind of reduce their contention opportunities. So the MU-EDCA parameter set essentially contains different parameters for each of the access categories that we have available for 802.11. So best effort, background, video, and voice. Each of them has the AIFSN and the contention window mean, max, and also a timer for how long this particular set is to be used after receiving a basic trigger frame. So the station in general enters the MU-EDCA parameter mode, if you will, after responding to a trigger frame with data frame from the access category for which it receives a successful response. So if your data for a particular IC is successfully received by the access point, then you enter the prioritized mode, and for an amount of time that is specified by the MU-EDCA timer. After that timer ends, you're free to go to single user or to the legacy mode. And that is to avoid cases where, say, the access point forgets to poll the station, and the station now is still with a very low priority parameter, so it's getting penalized because the AP being busy with something else. And then I think this is the last part for the channel enhancement, which is the RTS-CTS protection. So in a legacy, the enablement of RTS-CTS is autonomous. So every station is free to enable RTS-CTS anytime that they want for any reason that they want. And in general, it is either an implementation choice or there are some internal decisions based on the length of the PSDU that you want to protect. So it is an effective tool in overlapping BSS operation scenarios because you can reduce collision to hidden nodes and adapt to the presence of interference. But it's autonomous and it's localized at the station. But in the case of dense environments, it can create issues because if you think from the station's perspective, the station just wants to protect its frames and at the same time also minimizing incurring overhead because every RTS-CTS has some overhead coming with it. And the station doesn't have the best view of the network itself. It has the best view of its own. In dense environments, the access point is the entity that has the better view of the overall network situation because it sees all the packets that are being generated by all the stations that are operating in the BSS. It sees what is going wrong. It sees the payloads. It is always active as opposed to stations that can go to those states. So it has better visibility of if there is any occurring interference. So to kind of give the tools to the access point to enable the RTS-CTS employment by the stations, 11ax defined TXOP-based RTX protection, which essentially is a means provided to the access point to tell all the associated stations that they are required to use RTS protection for a given, if their TXOPs exceed a certain amount of time. That certain amount of time is provided in the HG operation information element, which is broadcasted to the stations in beacons, probe responses, and individually addressed responses. So by having this particular functionality, the access point can help mitigating collisions by having the stations always use the RTS-CTS, because in that case, the collisions are going to be avoided since you have enough protection at the receiver side as well. And the functionality is flexible enough in the sense that you can enable or disable it or change the parameters dynamically as the BSS progresses in its operation. So you can start by not having it enabled, and then at some point when traffic utilization and network utilization changes, then you can enable it. So in summary for part 2, so we kind of went over a lot of material related to aggregation in general, so how multi-TID aggregation works, how dynamic fragmentation works, and how it can be used instead of padding, the formats and the uses of compressed block ACK and multi-state block ACK frames. and all the functionality that we discussed about improving channel access and protection. So BSS color, MUDCA operation, two navs, the pixel-based RTS, CTS, and so on. So now, before going to part 3, so as before, so I have one question here that I can answer. So if you have any further question for this part 2 or for the part 1, that is, you can ask questions here, and then we can have a 3 to 4 minutes break. So the first question is there any source code generated in the development of the theory of the 802.11 standards? If so, what languages relied on in experiments? So there is no source code generated on standards. So standards are essentially, from an 802.11 perspective, you provide a set of rules, and then implementers and vendors and they take that particular standard, and when they build the code for their chips, they rely on satisfying those rules so that you ensure interoperability and cross-vendor operation to be 802.11 standards compliant. Now, to ensure the interoperability, there is also a Wi-Fi alliance that can tackle the part of ensuring that everything is performed correctly. So there's different levels of organizations, if you will, that can ensure that. But from an 802.11 perspective, there is no source code that reflects the set of rules that are provided in the standard. The next question is, will you be covering TWT? So yeah, the answer is yes. So that TWT is going to be part 3 of the presentation. So in 3 to 4 minutes when we start, I believe the first part is TWT. Okay, so I don't see any other questions. So then we can take a 3-minute break so we can reconvene at 10:52 Pacific time. All right. So we can start. Oh, you got a little bit of a stretch and some coffee. So part 3 and last part. So yeah, we're going to cover power save protocols. So the introduction of TWT, opportunistic power save, operating mode indication, and intra-PPDU power save from a power save perspective in 11ax. And then because of the introduction of the 6 GHz band in the 802.11ax PAR, there were some enhancements to active passive scanning and to the network operation that we will cover as well. So during this part, essentially, we'll addressing the power save protocols and the operation in the 6 GHz band. Anything that is related to improvements to power save, to power consumption in 11ax we'll cover, and also the enhancements in the 6 GHz band. So as is tradition, especially in major amendments, we always inherit as much as possible from baseline, so essentially legacy. So an 11ax device is on its own, an 11ac device, an 11n device, and so on, depending on the band of operation, of course. And then on top of that, we build improvements for that particular amendment. So from a power save perspective, 11ax inherited several legacy power save mechanisms, such as traffic indication mapping in beacons, PS polling, dynamic single mode power save, I believe it's the nomenclature here, APSD, and then in 11ax, the 2 sets of power save optimizations were introduced. One is TWT, which is classified as scheduled power save, and opportunistic PS and operating mode and intra-PPDU power save, which are unscheduled power save protocols. And we'll be covering all this, and we'll start with TWT. So TWT was originally introduced in 11A8 in a sub 1 GHz, and it allows an access point to manage activity in the BSS by scheduling stations to operate at different times. And it does so to kind of minimize the contention between stations, and at the same time reduce the amount of time that the stations need to be awake so that they can save power. We have inherited the individual TWT from 11AH and enhanced it with several ways, and additionally defined the broadcast TWT mode as well. From an overall perspective, the individual TWT is a mode that requires negotiation between the station and the access point, and we refer to the stations as TWT requesting stations and the access point as TWT responding station. Broadcast TWT does not necessarily require negotiation, although it is possible to negotiate broadcast TWT schedules. And the stations here are referred as TWT scheduled stay, and the AP is referred to as TWT scheduling stay. So from the terminology itself, you can realize a little bit of aiming at more scheduling in one part and not so much on the other. And that is due to the flexibility that the broadcast TWT has, that the schedules are being provided in a broadcast manner to the stations that are associated with the access point. So going with the element itself, inherited by 11AH as mentioned and enhanced by 11AX, and those enhancements are kind of identified in green here. So we do have 2 modes for individual TWT. One, the ITWT or individual TWT has only one parameter set, and the broadcast TWT allows the access point to include multiple broadcast TWT parameter sets in the same element. And as you can see, the format is a little bit more optimized with respect to individual TWT parameter sets. For example, the TWT field is 2 octets as opposed to 8 octets, which is in general the case for TWT. And that is because the broadcast TWT element is going to be included also in the beacon frames. So beacon frames are sent sporadically, but generally every 100 milliseconds. So we target to keep the beacon length as short as possible to minimize the amount of time for its transmission. So the individual TWT, you can negotiate multiple TWT sessions between two peer devices. Once you negotiate, you follow that particular session, and you can update the parameters or terminate a particular session at any time you want after the negotiation. And this is from individual TWT case. From the broadcast TWT case, the access point advertises on its own the presence of TWT schedules, and the advertisement occurs in beacon frames, for example, or broadcast probe responses, and tells you that these particular TWT schedules are valid for a specific term, and it can be for multiple beacon intervals. And any updates or terminations are notified by the access point in the beacon frame itself. So there is no need of unicast frame exchanges for updates and terminations. Now, as a station, once you receive the beacon, you can obtain the schedules in the beacon itself, and within those schedules, you can exchange frames with the access point. As mentioned, you can still negotiate broadcast TWT schedules with the access point, and this is done in general to tell the access point that among all the schedules that you have, I'm going to follow a subset of them, or, for example, the schedule that you have, the one that I'm wishing to join is not there, so please add it. So those kind of flexibility is added via negotiation. Both modes require implicit TWT signaling, essentially that everything is scheduled and known in advance rather than explicit every time to change it. And we have introduced the triggered mode for taking advantage of triggering within the service periods. So in terms of the TWT setup, which can be applicable to both individual TWT sessions and broadcast TWT schedules, essentially the TWT setup is the first part of the protocol. So you set up a particular session. You can identify what type of session you're trying to set up by the negotiation type. So if you set it, for example, to 0, then you're requesting an individual TWT session. And if you set it to 3, then you're negotiating a broadcast TWT schedule. The TWT element that is provided in beacons has its own negotiation type setting to identify a broadcast advertisement, and this is negotiation type 2. So when you are in the TWT setup phase, you are going to negotiate multiple parameters that are going to be used during your schedule or session. So when you are expected to wake up for the first target wake time, for how long you're going to be expected to be awake, what is the periodicity of your duty cycle, if you will. So this is via the TWT wake interval. And then the different modes that you're expected to operate during the service period. So you can have announced modes, so announced TWT, unannounced TWT, and trigger-enabled TWT. The differences between these three is that the announced one relies on the access points waiting for a PS poll or an APSD trigger frame from the station to declare that the station is awake in that service period. So relies on the station to announce itself on the service period. If the station does not announce to be in that awake in that service period, the access point just assumes the station is not there. The unannounced case is the other way around. The AP always assumes the station to be awake for that particular TWT service period, in particular at the start of the TWT service period. And given that it assumes the station to be awake, the AP can transmit to that station anytime during that service period. And the trigger-enabled case actually requires the access point to schedule a triggering frame from the station at the start of the TWT service period, so that even the announcement that is going to be requested from the station, for example, for the announce mode, can be sent in response to this triggering frame, so that the station doesn't have to wait and contend for sending uplink frames. So once the setup is performed, all frame exchanges between the AP and the station are expected to occur within the TWT service period. And outside of the service period, the stations are expected to be in those states and recommended to not transmit to the AP. However, since this is a recommendation, as a station, you can still wake up outside of the service period and transmit to the access point. So in terms of individual TWT, from a setup perspective, we have two ways of setting up, one which is AP controlled and one which is stay initiated. So the AP controlled is the unsolicited case. So the access point tells the station, okay, we are going to set up a TWT session, and these are the schedules. And essentially, there is no expectation from the station to essentially reject this particular session. However, as a station, you can still tear down and not operate in a mode. So this is essentially to give flexibility to the access point to allocate the stations in a time-coordinated fashion so that it can maximize the resources. The other case is the solicited TWT setup, which is essentially initiated by the station. So that the station tells the access point, okay, I want this particular periodicity, this particular durations of time, and so on. And the access point can either confirm or tell the station an alternative schedule that may be satisfactory to the station. So you have different ways of setting up your schedules. Broadcast TWT, on the other hand, relies mainly on announcements. So the access point simply announces the schedule that it plans to keep for that particular BSS, and the stations can join that particular setting or request the access point to schedule others. And they are always advertised in beacons so that everybody, without the need of negotiating anything, they can know where the schedules are going to occur during those beacon intervals. There is also a sub-mode for under broadcast TWT, which is the negotiation of a listen interval between the station and the access point. So traditionally, the listen interval is specified by the access point in multiples of beacon interval, and to tell that, okay, I'm expecting you to wake up every, for example, 5 beacons to read any information that I'm providing in the beacons. The listen interval negotiation is providing the flexibility to the station to tell to the access point, instead of every 5 beacons, I'm planning to wake up every, say, 10 beacons. So that's essentially the difference. So instead of negotiating broadcast TWT schedules, you're negotiating TBTT intervals, which are target beacon transmit times. So once the negotiation is concluded, the main portion of your behavior is going to be within a TWT service period, and depending on the modes. But in general, for example, for the trigger-enabled TWT, the access point is expected to schedule a triggering frame so that the stations can declare their awake state by responding to that triggering frame, for example, with a PS poll. And then eventually also provide buffer status report for their uplink so that the access point with that first phase of polling can determine the availability of the station in that service period and how to allocate the resources to that station or also to the other stations that are in that are awake in that service period. And of course, depending on the availability of the stations and the traffic that is pending for those stations and the traffic that is being advertised by the stations for the uplink, the access point can determine how to arrange the resources in the downlink and uplink to maximize the delivery of the traffic while minimizing the amount of time that the stations have to spend in the awake state. So once the TWT service period ends, the stations are free to go to power save, so they can go to those states so that they can save power. And if the traffic is ending before the estimated TWT service period end time, the access point can also tell the stations that they can go early in those states. And I will go over that in the next slide. But outside of the service period, as I mentioned earlier, the stations should not transmit outside of those service periods. So early TWT service period terminations are indications by the access point in general to the station to tell the station, okay, so we're done during the service period, so you're free to go. If there is no such indication by the access point, in general, the station is required to stay awake until the end of the service period. There is one case where the early TWT service period termination can be indicated also by the station, and that is by using a TWT information frame. The TWT information frame has a little bit more functionalities on top of the early TWT service period termination, and we will cover it in the next slide. But so, yeah, in general, there is a signaling from the access point to tell the station, you're good to go, we're done, you can sleep. So the additional functionalities that I was referring for the TWT information frames are, in general, resumption and suspension of TWT schedules. So in general, since the schedules are periodic, the station is required to follow this periodicity unless explicitly stated otherwise. That explicitly stated otherwise is being done with TWT information frame. So let's say that you have periodic traffic for the next 5 minutes. You set up a TWT schedule, and then instead of terminating the TWT schedule with the risk of not having that schedule anymore with the access point, you want to suspend the schedule. So to achieve the suspension, you send a TWT information frame telling the access point that, okay, I'm going to suspend the schedule. And you can either tell the access point for how long you're suspending the schedule, or you can simply say until further notice. So when you have the until further notice, it's a suspension because you don't know when it's going to be resumed. And it's essentially a reschedule when you know when it's going to occur. So now if you have suspended, you would need another TWT information frame to be sent to the access point to resume that schedule again. And when you send it, you indicate at which target wake time you're going to resume the schedule. So this kind of functionality is available from both the station's perspective and the access point's perspective. So you can achieve it bi-directional. So that is from a TWT perspective. Opportunistic power save, one of the modes relies on TWT, which is the scheduled version. And there is another mode, which is the unscheduled opportunistic power save, which does not rely on the TWT, on the broadcast TWT. So from a scheduled perspective, the access point enables scheduled OPS by essentially allocating a service period during a beacon interval, saying that, okay, this is going to be an opportunistic power save schedule that we're going to rely during the service period. And this is signaled by essentially using a field in the element, in the broadcast TWT element of the beacon. You set it to 3 and the broadcast TWT ID field to 0 to indicate that this is an opportunistic power save schedule. Broadcast TWT ID field equal to 0 indicates a broadcast schedule. And this recommendation field specifies this particular functionality, which is opportunistic power save, or let's say scheduled opportunistic power save. The opportunistic portion comes from the fact that the access point at the start of the service period sends a team or an OPS or a field discovery frame. These are in general management frames that contain an OPS element, which tells the stations that are identified by the team indication element. So there is a list of stations to tell them that, okay, so during this service period for this amount of time, you're not going to be scheduled. So you can do whatever you want during that time. So team information element and OPS element in that particular frame tells that set of stations to not interact with this AP for that amount of time, which is identified by the OPS period. Now, during this OPS period, the stations are not expected to exchange any frames with the access point. And likewise, the access point is not expected to exchange any frames with those stations. This ensures that the station can go to those states for that amount of time and essentially come back after the OPS period ended. So between the two modes, the unscheduled OPS is very similar to the scheduled OPS, except that the AP does not advertise in advance in the beacon when these action frames are scheduled to be delivered. So the station is expected to be awake and waiting for these action frames to come without knowing when they are going to come, which is not the case for the scheduled scheduled OPS, where the access point tells in advance in the beacon that this action frame is expected to come in, say, 3 seconds. So going to intra-PPDU power save, this is also an opportunistic power saving kind of mechanism. So the idea stands on, and it can actually be used by stations that are in active mode and power save mode. So in general, we do not expect stations, from a legacy perspective, stations that are in active mode, we expect them to be awake at all times. With intra-PPDU power save, actually, that's not the case. We do allow also stations in active mode to be unavailable if during the PPDU duration that satisfies certain criteria. So the criteria for the PPDU to satisfy are essentially obtained from signaling that is present in the PHY header of the packet of the PPDU. So we have the BSS color that we mentioned earlier to differentiate between intra-BSS and inter-BSS PPDU. The PHY header in the SIG-A contains an uplink flag, which additionally helps differentiating downlink PPDUs from uplink PPDUs. And we do have also the stay ID in the SIG-B that can help determining if the stay is the intended recipient. So with this set of fields in the PHY header, the station can essentially decide to save power by entering those states or being unavailable after the PHY header until the end of the PPDU if the PPDU is identified as an intra-BSS PPDU. So the reason why the station can go to those states within an intra-BSS PPDU is that if the access point or any other station in that PPDU is in that DSS is actually sending a PPDU, then the likelihood of the access point sending a PPDU again to this particular station is close to zero, because that PPDU that is over the air already is either intended to the access point or is being generated by the access point. So the station can essentially can go to those states until the end of the PPDU. So now the duration of the PPDU itself is indicated in the PHY header itself, in the LSIG portion of the PHY header. So one part that is noteworthy to mention is that even though the station is allowed to enter those states until the end of the PPDU, it still needs to continue counting down its nav timers so that after the PPDU, it doesn't wake up and starts transmitting on top of other exchanges. Forget that it went to those states because of intra-PPDU power save. And if it wakes up immediately, and of course assumes that after going to those states and okay, so I'm having an issue. I cannot move to the next slide. Let me see if I can do it with. Okay. Okay, yes, I'm having issues to move to the next slide, so I'm asking if previous slide, please. Okay, now it's working. Okay, so having finished with intra-PPDU power save, so the last power save mode that we're going to cover is operating mode indication. The operating mode indication does not really rely on going to those states or unavailable to save power, but it relies on fast switching of operating parameters to achieve power consumption reduction. So say, for example, a station is operating with 4 antennas and is using 4 spatial streams. And at some point, the traffic that is being generated does not require 4 antennas. What the station can do is notify the access point that the number of antennas on the receive side at the station is decreased to 1. And as such, it can turn off the components of the other 3 antennas. So it can save power by essentially reducing the number of spatial streams and or the channel width, for example. So this particular functionality is achieved with operating mode control field that is also carried in the HT control. It contains several parameters that the station can play with to achieve different functionalities. So the first 3 are the ones that I mentioned. So RxNSS, which is essentially maximum number of spatial streams that the station can receive. So you can turn it up and down depending on available data or the available antennas that you have. The channel width can be reduced or increased between 20 to 160. And the TXNSS as well can be modified to indicate how many spatial streams do you support in transmission. This is particularly useful for the trigger-based PPDU case, where the access point is the one dictating the NSTSs for the TV PPDUs. There are additional functionalities that are embedded in this particular control fields. One is uplink MU disable. So the station can dynamically enable or disable uplink multi-user operation depending on its needs. It can also enable or disable the extended range single user mode, which is a mode that was discussed yesterday during the PHY presentation, which is essentially a PPDU that provides an extra link budget gains of, I believe, 3 to 5 dB. However, the use of the extended range single user PPDU increases the PPDU duration for the same amount of data, and as such can be enabled or disabled from a particular recipient. Say, for example, that the transmitter is using it more than necessary. So if this, for example, if the transmitter is very near to you and keeps using extended range single user PPDUs as opposed to using high efficiency PPDUs, then the receiver can tell the transmitter, okay, I'm disabling extended range SU, so go use high efficiency PPDU formats. And there is also downlink MU-MIMO resound recommendation, which suggests increasing sounding frequency and the disablement of the uplink MU data operation as well. So that's from a power save perspective. So now going to enhancements for the 6 GHz operation. So the 6 GHz band became free or open for discussion for becoming free for use for 802.11 kind of midway while 802.11ax was being standardized. And so it came, if I recall correctly, around draft 4.0. So these design goals came essentially at that part of the project. And so the goals were essentially to minimize or reduce issues with well-known issues that were occurring in from a legacy perspective. And given that the 6 GHz band is going to be a greenfield band, trying to minimize those issues for the First Amendment as much as possible. So the first goal was scanning phase. So we generally have probe storms to deal with in the 2.4 GHz and possibly in the 5 GHz. So to kind of minimize the channel pollution in the 6 GHz band due to the controlled active scanning and to reduce scanning latency. There were different functionalities that were either mandated or specified for the 6 GHz band to minimize channel pollution. We'll go over those a little bit more in detail, but the simplest thing that you can think is first try out-of-band active passive scanning. Out-of-band meaning 2.4 or 5 gigahertz. If you find something there, then move to the 6 gigahertz band to associate with that particular BSS that you found. Or if you didn't find it, then use in-band scanning. The other part was association and authentication phase. Also here, minimize channel pollution and association latency. Similarly, instead of using the 6 gigahertz band, first try on-channel tunneling in the 2.4 or 5. So perform the association and authentication in the band that you're currently in, as opposed to going to the 6 gigahertz band and finding the access point and then associate and authenticate to that access point. And of course, transmit power control, not only from a regulatory perspective that is going to be required and that is being required, but also for increasing the natural spatial reuse and scaling for dense networks, which is essentially achieved by mandating an existing transmit power control mechanism in the 6 gigahertz band. So we'll cover a little bit more in detail of this part, and starting with the scanning phase. Scanning phase is discovery. So you're a station that is scanning different channels, trying to find an access point, and in general, you can perform either out-of-band scanning or in-band scanning. Out-of-band scanning is in the case of co-located APs, like access points that are advertising the presence of other APs in the other band. If you find, for example, that if you're scanning the 2.4 gigahertz band and an access point is saying that, hey, there is a 6 gigahertz AP operating in that particular channel, and you discover it, that's out-of-band scanning. So to avoid the station going to the 6 gigahertz band and start scanning, first goes to the 2.4 or 5 gigahertz band, whichever it supports, to find out if any of the candidate APs of the 6 gigahertz band are discoverable by this means. And this is achieved by requiring APs that are operating in the 2.4 gigahertz and 5 gigahertz and that are co-located with 6 gigahertz APs to advertise the presence of their co-located 6 gigahertz APs. So there is a certainty that the station can achieve this information in the 2.4 and 5 gigahertz. Then the alternative is the in-band scanning, where you go and scan all these 6 gigahertz channels. However, here to minimize the adverse effect of active scanning in terms of channel pollution, the channels were divided into preferred scanning channels and non-preferred scanning channels. Essentially, 1 in every 4 20 megahertz channels is a preferred scanning channel, so that the station can scan first the preferred scanning channels to find the access point without polluting the non-preferred scanning channels. So if the station is in a channel, it is required to listen for about 20 milliseconds. So it's 20 TUs, where 1 TU is 1,024 microseconds. And the station does not have any prior knowledge of that access an access point on that channel. Then, depending on whether the station is scanning a PSC or a non-PSC, there are different rules. So if it is a PSC, then the station is allowed to probe, so active scanning. If it is not PSC, then the station cannot active scan. So it needs to still continue passive scanning. This is done so that uncontrolled probing in the non-PSCs is not possible in most of the cases. So out-of-band scanning in general relies on the reduced neighbor report element. So this is an element that APs that are operating in the 2.4 or 5 gigahertz, including the beacons, and essentially provides a kind of a short summary of the information of APs that are operating in the surrounding. Those APs, for our particular purpose, are those that are operating in the 6 gigahertz band and that are co-located with the AP that is reporting or that is including the RNR. So the access point provides different information about the 6 gigahertz AP, so that the station, once it is received this information, has as much information as possible to go to the 6 gigahertz band and the complete discovery and association with that particular AP. So now, because this is a reduced neighbor report, it means that the length was aimed to be as short as possible, so you don't have the complete information. So to obtain that complete information, you can either send a probe request to the 6 gigahertz AP itself, or probe the collocated AP that is reporting through OCT, for example, to essentially determine what are the full, for example, capabilities, operation mode parameters of that particular AP. Or you can do passive scanning in the 6 gigahertz band itself. So that is from an out-of-band scanning. So once you failed, let's say, to discover via out-of-band scanning, then you can go to in-band scanning, and you go first over this reverse scanning channel. You scan them. They are once every 4. So every 80 megahertz, you're going to find one reverse scanning channel. And as mentioned earlier, you can only active scan over PSC channels and not over non-PSC channels. On top of it, in general, for 2.4 and 5, we do not have rules as to what are the probe requests frames that you can send. So the station is kind of free to even broadcast and solicit probe responses from all those APs that are in the surrounding, which is what causes a probe storm. Because one station, for example, that sends, let's say, a probe request in a conference venue, you will have responses from, let's say, 20 APs that are in the surrounding. And those 20 APs probe responses are essentially clogging the medium. And you can do this multiple channels, so exacerbating the problem. So to limit those kind of issues, there are requirements in the 6 gigahertz band in terms of how many probe requests with wildcard SSIDs you can send, or wildcard is essentially unknown SSID, and unknown means that anybody has to respond. So, for example, the simplest one is you cannot send a probe request that you don't know the SSID and you don't know the BSSID. So a blind probe request that would cause everybody to respond. And also there are limitations in terms of how many probe requests you can send to a particular BSS or to an unknown BSS, or whether you can send a probe request to an AP that you already have discovered. So there are limitations that aim at avoiding active scanning issues such as the probe storm that I just gave as an example. So the next part, which is the transmit power control. Transmit power control is it's a mandatory mode in the DFS channels in 5 gigahertz. So it is required in the 6 gigahertz band in general, and it relies on the transmit power envelope element that is carried in the beacons, probe responses, and so on. And it essentially conveys local or regulatory maximum transmit powers that are going to be applicable to all the bandwidths that are supported by the DSS and the channel configurations of the DSS. And we have 2 different ways of providing this information. It's either with ERP for a given full bandwidth, and we can have different combinations of 20, 40, 80, 160, or as a power spectral density, also in this case ERP, for each of the 20 megahertz subchannels. So the second mode essentially allows even a non-uniform distribution of the power over the bandwidth. So in terms of behavior, the station, once it sees that an access point is providing transmit power limitations via this transmit power envelope, is required to follow transmit power control, essentially to reduce the transmit power to the maximum transmit power that is advertised by the access point, as long as it's associated with an access point operating in the 60 gigahertz band. Or if it is not associated, but it intends to send an SUPPD to a particular AP that is advertising TPC requirements, also in that case, it's required to follow TPC rule. So essentially to not exceed the transmit power. So, and I believe this is the last part, which is the HE-BSS operation in the 6 gigahertz band. So there are some additional enhancements that were introduced because of the greenfield opportunity, if you will, of the 6 gigahertz band where there were no legacy 802.11 devices operating. So to kind of keep the spectrum clean, there are rules that specify that a station that operates in the 6 gigahertz band cannot operate as a pre-11ax. So for example, you cannot have an 11ac device operating in the 11ax band. So you have to be an 11ax device. And also you can only transmit non-HT duplicate PPDUs and HT PPDUs. So you cannot transmit other types of PPDUs, for example, VHT PPDUs, HT PPDUs, DSSS PPDUs. So the reason why these two were chosen was that the HT PPDUs is the most efficiently available PPDU up to date. And the non-HT duplicate PPDU is the one that has the least possible overhead from a PHY header perspective, and also allows correct reception even if you're operating in the 20 megahertz mode only. Beacon generation, similarly, so we generally generate beacons in non-HT PPDU format because of legacy presence in 11ax, given that all 6 gigahertz stations are going to be 11ax devices. The beacon is also allowed to be carried in an HE-SU PPDU as long as it's using mandatory MCSs and the 20 megahertz bandwidth and NSS equal to 1, which are parameters that are required to be supported by default by all the stations. So all of them can support the reception of the beacon. Similar considerations for the field discovery and the probe responses. So these frames can be carried in a broadcast RU of an HE-MU PPDU, but also in this case, they have to be located in an RU that can be decoded by all the stations in the BSS, which is essentially the primary 20 megahertz. And also here, there is a requirement of basic MCS and NSS equal to 1. And another part that in order to allow switching between different bands, channel switching protocols also are required to be supported for 6 gigahertz stations, which is not the case in general for amendments prior to 11ax. So with that, so in summary, we covered the different variants of TWT operation, how opportunistic power save, intra-PPDU power save, and operation mode operation works. How to discover APs operating in the 6 gigahertz band, covering both in-band and out-of-band scanning with the different flavors of active and passive scanning, and the additional enhancements that were introduced for the 6 gigahertz band. So with that, we're done. So I'll take some of the questions that I have here. So the first question is, in 6 gigahertz, FCC requires that the client has an indication that the AP is operating on the 6 gigahertz channel. Does this mean that the client cannot send probe requests without first getting an RNR report on the 2.4 and 5 gigahertz channels, or getting a beacon, etc., on the 6 gigahertz channel? I.e., autonomous scanning is no longer permitted. Is this true even for PSC channels? So I cannot speak from an FCC perspective. The latest rules, at least to the best of my knowledge, they haven't narrowed down everything, unless I'm out of date on their progress. But from the IEEE 802.11 perspective, you are allowed to send or to do autonomous scanning, essentially active scanning, in the preferred scanning channels, even though you didn't do the 2.4 and 5 gigahertz scanning first. So as usual, the regulators, they do add additional restrictions possibly in certain behaviors. And it is possible that FCC might take that route for the 6 gigahertz in general. But yeah, to the best of my knowledge, I mean, I'm not aware of the latest status that they have on that aspect. The next question is, how in-depth has the past 2 days covered the 802.11ax standard as it is published? And the question is for the, so this training is essentially aiming at providing a general overview of the main features. So you can think of it as to get an idea of the development of the standard, what the issues were trying to be solved, what different protocols were being defined for those improvements. You have a very good knowledge of those particular functionalities and the expectations from these features. But for example, if you want to go into the deep dive details, for example, of taking, for example, a simple mode uplink MU operation, there are some minor rules that are not covered. For example, how trigger frame solicitation of trigger-based PPDs from a multiple BSSID set. Those are not covered. Those are second or even third level of details. So the next question is, I'm taking away from the discussion that there are several options when implementing the 802.11ax protocol. In this case, are there a strict set of parameters that have to be implemented to be certified as Wi-Fi 6? So that's a good question. In general, and I'm not going to focus on 11ax in particular in my response to keep it as generic as possible for different reasons, but from an 802.11, it's tradition to have different ways of tackling a particular issue. And then when you go to another organization, depending on the discussions that go, they can decide to narrow down the testing on a specific particular mode or option so that they ensure, for example, interop among vendors for that particular mode and do not cover the other modes. That does not mean, though, that the implementations or other vendors are not implementing the other modes. It's just that they are not tested to the extent of interop. So the question 10 was unfinished. It just says FCC regulations. I'm not sure what the question was. But yeah, that's about it. From what I see, there is one citation of the FCC regulation, which I cannot see for some reason. Oh, okay, so it's a citation of the FCC case as of now, which seems to be in line with you're not really allowed. Yeah, so based on that particular reading, which seems to be in line with what was there earlier, is that you can probe if you know that an access point is operating on that particular channel. And that's about it. I don't see any further questions. So I'll ask Jennifer if she wants to take over. And thanks everybody for attending. This was also very instructive for me.
Thank you very much, Alfred, and thank you again, Ben, and thank you to everybody, all our dedicated attendees who stayed today and yesterday as well. We very much appreciate your time and attendance. And just a reminder, if you could please complete that survey. We'd love to hear your feedback on this event to help us plan for future events. And once again, we thank you for your time and have a great day.
Thank you. Bye.